Welcome back to the deep dive. You know, human civilization is built on this one core, almost religious assumption
Right.
that progress, especially scientific and technological progress,
Mhm.
is infinite, that it goes on
That
forever,
the frontier will always be pulled forward. Yeah.
always, by this expanding light of knowledge. But today, we're going to take that foundational belief and run it through a pretty rigorous, cold mathematical model.
A very cool
We're going to be
model.
examining the hard limits. And these are limits imposed not by funding or politics or resources, but by human biology and cognitive capacity.
That's exactly right. We are tackling a profound and I think a genuinely uncomfortable question today, and it's derived from Stanislaw Lem's seminal work, Summa Technology.
Incredible piece of work.
It's a masterclass in predictive theory, and what we are extracting from it today is just an incredibly clear, multi-layered argument that suggests this age of ours, this age of exponential, unrestricted growth is fundamentally transitional.
Transition. So it's a phase.
It's a phase. It has
Yeah.
a finite lifespan.
So our mission for this deep dive is, well, it's crystal clear. We are trying to determine whether rational activity, which Lem defines as technoevolution,
Right.
is a sustainable, dynamic process that's always striving for unlimited expansion. Or if it just changes. If it changes so fundamentally upon hitting its natural mathematical ceiling that it loses all resemblance to the explosive, creative form that we recognize right now.
And we have to, right off the bat, distinguish this kind of analysis from many of the other grand cosmic speculations we sometimes get into.
Okay, how so?
Lem makes this critical distinction, when he discusses the possibility of stellar civilizations or intergalactic travel in his other works. He's very clear that those predictions often rested on a pyramid of hypotheses.
A hypothesis on top of another hypothesis.
Exactly. Layered upon other hypotheses, you might have 10 layers of if-then statements, which makes the ultimate probability of it happening
Pretty low.
very low. It becomes speculative fiction in a way.
But this analysis is different.
Completely different. This is a forecast that's built on foundational, thoroughly studied facts. We're talking about verifiable trends in publication rates, in population growth, in human physiological limits.
So we have objective metrics, we have the data.
We have the data, precisely, because we're looking at established rates of information accumulation and resource consumption, and specifically the consumption of human intelligence. Lem argues that the probability of these eventualities occurring is, and this is his quote, immeasurably higher than those broader cosmological discussions.
Because we can see the curve.
We can see the curve bending based on data that we already possess.
It's just so easy, isn't it, when you look at the last 300 years, to assume that the growth of knowledge will just eternally pull technology forward at an ever-increasing pace.
It's our default setting.
It is.
Both.
But this analysis, it suggests that this avalanche-like pace of cognition, this constant doubling of information, has an absolute ceiling. And here's the really unnerving part. The mathematics of human constraint suggest we may be approaching it much sooner than most people, or frankly, even most scientists currently anticipate.
And to really understand that, we need to set the stage for this, this inevitable conclusion by first understanding the engine itself.
Right.
You can't predict the burnout of a system until you fully grasp the fuel and the feedback mechanism that, that created the explosion in the first place.
Okay, so let's unpack that. Before we even talk about the ceiling or the crash or this inevitable deceleration, we have to look back at the historical engine.
We have to.
This 300 years of exponential scientific explosion that got us to this precarious point.
It's an origin story, and it's one that goes back far, far further than the 17th century Industrial Revolution. The spark, the root of inquiry, it goes deep into the Babylonian and Greek eras.
And it's interesting because we often assume that technology creates science, but historically the reverse is often true, isn't it?
Much more often than we think,
Yeah.
yes.
So what was the initial motivator? I love this part of the source material. Lem references Einstein, who gave this amusing but, incredibly accurate answer to the first cause of science itself.
Nobody scratches unless he itches.
Exactly. The need. The itch was the fuel. Science was fundamentally driven by societal needs, whether they were practical, military, philosophical.
All of the above.
And those needs became the engine that drove technology forward.
But we have to clarify that distinction a bit. Societal needs drove the expansion and the acceleration of science, for sure. But they didn't actually create the fundamental scientific method itself or the earliest theoretical structures.
Okay, so the itch provides the gas, but it didn't build the car.
That's a great way to put it. Those roots were truly abstract and conceptual. They were far removed from any immediate industrial application.
Which brings us to this fascinating idea of the birth order of the natural sciences. Lem posits a really clear hierarchy based on complexity and, well, abstraction. So where did it all begin?
It began with the most distant, and you might say the most abstract field imaginable: astronomy. The study of the grand, predictable, clockwork mechanics of the heavens.
And this primacy is absolutely key, right?
Oh, it's everything. Because the grand regularities of celestial mechanics, the fact that you could predict an eclipse years in advance, spurred the creation of abstract mathematical systems that ancient technology simply did not need.
That is such a crucial detail. I mean, an ancient engineer, they needed basic arithmetic, right, for measuring areas, for constructing a pyramid, or calculating crop yields.
Simple stuff.
Yeah. They didn't need complex, abstract geometry to build a basic irrigation system.
Absolutely not. The predictive power of astronomy created a need for intellectual tools that far exceeded basic commerce or construction. The Greeks, for instance, they created these rigorous axiomatic systems, like Euclidean geometry, they were pure intellectual frameworks, perfect, non-empirical structures.
And meanwhile, you had the Babylonians developing this sophisticated arithmetic that was completely independent of geometry.
Exactly. And this theoretical depth, spurred on by trying to understand the heavens, is what historians recognize as the true beginning of the scientific journey. It wasn't about building a better pot.
It was about understanding the universe.
Yeah.
So astronomy provides the foundational concepts, the need for abstract math, and that initial scaffolding for rational thought. So once that intellectual framework is in place, what happens next? What's the next discipline to emerge?
Well, following astronomy, the questions it raised about forces and motion and matter, what is this stuff we're standing on, led directly to the emergence of experimental physics.
So it comes down to Earth.
It comes down to Earth. Physics took that abstract mathematical rigor from astronomy and applied the experimental method to earthly phenomena. It started testing things.
Okay. And once physics had established the foundational rules of matter and energy, the focus,
Yeah.
it naturally narrows even further.
Yes, from the very big to the smaller. Physics led directly to chemistry, the study of molecular interactions and transformations. And you couldn't have chemistry without the tools and the conceptual depth that physics provided.
And
Finally, the very last natural science to emerge from what Lem calls the fog of concepts impervious to checking.
I love that phrase.
It's brilliant, isn't it? That vast, complex field of unpredictable variables, that was biology, which only truly consolidated itself as a rigorous science at the turn of the 20th century.
And it could only do that because it was standing on the shoulders of the others.
It was utilizing the advanced tools and the chemical knowledge that had been developed by its predecessors. You can't understand DNA without understanding chemistry. You can't understand chemistry without physics.
That sequence really emphasizes how science progressed, doesn't it? From the most orderly, distant phenomena, the stars, to the most chaotic, intimate phenomena, which is life itself.
Yeah. It needed the clean rules of physics and chemistry before it could even begin to tackle the sheer complexity of a single living organism.
And this is so important. We have to recognize that the two essential elements needed for the future exponential explosion.
The mathematical spirit and the material tool.
Right, the conceptual depth and the experimental method. They already existed in an embryonic form before the Industrial Revolution.
They were waiting in the wings, so to speak.
Which brings us to the 17th century. The Industrial Revolution didn't create the parts, but it assembled the engine. It flipped the switch. It solidified the positive feedback loop.
Absolutely. The massive scale of manufacturing and the new social needs of industrialization, they gave science this unprecedented momentum. It united theoretical knowledge with immediate practical application on a scale never seen before.
And for the last 300 years, technology has been linked to science by this robust and crucially self-amplifying mechanism.
Self-amplifying, that's the key.
Let's break that mechanism down in detail, because this is the 300-year engine we're talking about. How exactly does that loop amplify itself?
It starts simply enough. Scientists deliver theoretical discoveries to technologists and engineers.
Pure research.
Pure research, exactly. Now, if those theoretical results prove immediately fruitful, if they lead to, say, a new material or drastically improved efficiency in a steam engine, Or an entirely new tool like the internal combustion engine or the radio,
Big win.
then research in that specific area is immediately amplified.
And by amplification, we mean money, we mean prestige, we mean infrastructure, and most importantly, more human capital, more minds on the problem.
Exactly. More funding, more people dedicated to that sector, larger laboratories, and concentrated political attention. It's a very rapid, self-reinforcing cycle. But the source notes something really fascinating and asymmetrical about this loop, and it explains its relentless forward drive.
The asymmetry being that negative feedback doesn't actually stop the theoretical engine.
That is the secret sauce to its success. Let's say a purely theoretical discovery is made, abstract quantum mechanics, for example. If the initial reaction from technologists is negative, if they dismiss the concept as impractical or just esoteric or way too expensive to ever implement, that negative attitude does not mean the theoretical research in that direction stops completely.
It just keeps going.
The theoretical engine keeps running. It's driven by pure curiosity and intellectual need. It keeps generating new information regardless of its immediate utility.
So even if the amplification from the positive feedback loop is missing, there's no immediate new steam engine or transistor out of it, the scientists just continue to produce new, potentially world-changing knowledge for its own sake.
Yes. The only thing the negative feedback prevents is the speed of implementation, not the creation of the theory itself.
That's a huge distinction.
It is. This asymmetry, where theoretical research is constantly generating output, regardless of technology's immediate capacity to absorb it, that's what has allowed science to maintain such a relentless forward trajectory for 3 straight centuries. It's a system that is designed almost perfectly for constant explosive growth. So if we accept that science is fundamentally the process of acquiring information and producing knowledge,
Which seems fair.
then the rate of its development is most accurately measured by the amount of information it generates. And this is typically quantified by the number of scientific publications released globally.
Okay.
What's truly astonishing here is that this immense historical growth follows a very specific mathematical curve.
We are talking about the exponential law.
Yeah.
This is where the volume of scientific output, the number of publications, the quantity of new data points, it doubles over time. And the time it takes to double is, frankly, alarmingly short.
Precisely. This is the definition of exponential growth. A set grows faster precisely because it is already numerous.
It feeds on itself.
It feeds on itself. In the scientific context, every discovery acts as a kind of nucleus that then generates a series of new proportional discoveries. If you have 1,000 discoveries, they might generate 100 new lines of inquiry.
Right.
But if you have 10,000 discoveries, they generate 1,000 new lines of inquiry. The system feeds itself, and the growth rate accelerates with the size of the total knowledge base.
And this sounds almost miraculous, doesn't it? A self-perpetuating engine of knowledge. But the very nature of exponential growth, when you look at it across history or nature, it suggests it can't last forever.
It never does.
We need to introduce the analogy that puts this extraordinary scientific pace into perspective.
The bacterial colony analogy it's perfect for understanding why this is just a transitionary phase. Think about any system in nature. An embryo, a tumor, a colony of bacteria on a culture medium in a petri dish. They all grow exponentially.
But only for a short time.
But only for a very short, very specific period. And why is that?
Because the environment itself quickly imposes limits. The petri dish runs out of food, right?
Yeah.
The waste products accumulate, and the colony basically chokes itself.
It chokes itself. The system inevitably turns that beautiful exponential growth curve linear, or it halts it entirely. The party ends.
Yeah.
And the source text offers this really terrifying little thought experiment. It says, just calculate how quickly a bacterial colony would digest the entire mass of the Earth if its exponential growth were unrestrained.
And the answer is?
It's a matter of weeks, maybe months. The planet would be gone.
Which is a truly fun and also terrifying metric of non-sustainability. But this is where we get to the grand contrast, which makes our current situation so unique in history.
The contrast is stark, and it is singular. The development of science, when measured by the accelerating number of publications and discoveries, is the only known process in human history that has successfully maintained this astonishing, explosive, exponential pace for 300 years.
Without hitting a hard external environmental limit.
At least not until now. The limit, it turns out, isn't in the petri dish, it's in the cook.
It's in the person looking at the dish. And we can grasp the sheer magnitude of this surge just by looking at the data points that were available to Lem when he was writing this.
They're staggering even then.
At that time, there were already about 100,000 scientific journals being published globally, which is already an unmanageable amount of reading for any one person.
You couldn't even read the abstracts.
No way. And if that constant doubling time continued, which remember it had been doing for centuries, the historical prediction noted in the source text was just staggering. The number would reach 1 million journals by the year 2000.
1 million. Think about that acceleration. That prediction, I mean, even if some of that output has now shifted to non-journal digital formats, it perfectly captured the frantic, overwhelming scale of the information deluge we're living in.
1 million distinct publications, all claiming to advance knowledge, all demanding attention, synthesizing data, suggesting new lines of inquiry. The knowledge base is multiplying at an absolutely insane rate.
It is.
So, if the system is so robust, and the Earth hasn't run out of money or paper or server space, where is the natural limit? What stops this?
This is the turning point of the entire argument. The limit isn't a physical resource constraint in the environment. It is the ultimate non-negotiable biological constraint.
Cost.
The human being required to generate, to process, to understand, and to synthesize this exploding volume of information. The most essential resource is the human mind itself.
And this is where the argument really pivots from, mathematical physics to profound sociology and cognitive science. We are moving from the sheer speed of publication rates to the very practical staffing requirements of the scientific enterprise.
Exactly.
And this is where it gets really interesting and, well, potentially a little dystopian.
The limitation isn't simply funding or, the capacity to run experiments. It's the finite biological capacity of the human research pool.
Now, the number of scientists is also growing exponentially, but logically, its doubling rate has to be smaller than the doubling rate of the knowledge they produce. But even accounting for that difference, the math still leads to this absurd, completely impossible conclusion. This is what the source calls the calculation of doom.
And this is the linchpin of the whole predictive argument. It's so simple and so devastating. If the current rate of scientific growth, that is, the demand for new researchers just to keep pace with the exponential information curve, were to continue, Lem's analysis determines that within a remarkably short time, about 50 years from the time the work was composed, every single resident of Earth will be a scientist.
Every person on the planet. Infants, the elderly, people dedicated to completely unrelated manual or artistic labor.
Farmers, poets, bus drivers.
The entire 7+ billion population of Earth would need to be professionally engaged in scientific research just to keep the current exponential curve running.
It's a beautiful, elegant absurdity, isn't it? It defines the mathematical impossibility of the curve continuing. This is the absolute ceiling. It is logically, physiologically, and sociologically impossible to surpass this limit. Unless, and this is the very wry aside in the source text, one person could simultaneously embody several scientists.
And that's the moment the bubble bursts. The conclusion is just undeniable. Exponential growth in science will be curtailed, and it's due to the fundamental lack of human resources to staff it.
It's a deceleration that's imposed by biological necessity and basic arithmetic. There's no way around it.
But this is where we have to introduce a potential modern counterpoint, right? Because I know what you're thinking. You're asking, wait a minute, that prediction doesn't account for machine learning, big data analysis, and AI.
The elephant in the room.
Right. Can't we effectively embody those several scientists through automation?
It's the critical challenge to the thesis. If we can delegate the menial tasks, sorting publications, running trillions of simulations, basic analysis, doesn't that fundamentally break the human mind barrier?
What does the underlying premise say about these non-biological solutions?
Well, the premise holds up surprisingly well, actually, even when you consider advanced automation. While an AI can certainly manage the volume of data, it can read those 1 million journals in a second, it struggles with the crucial human tasks. Such as defining the next genuinely new question, synthesizing concepts across vastly disparate fields, taking an idea from biology and applying it to astrophysics, and exercising truly fundamental, non-directed curiosity.
So in other words, AI helps us manage the complexity of the current knowledge base, but the human is still the bottleneck for creating the next paradigm shift. The truly unforeseen theoretical leap.
Exactly. The human mind is still required for the high-level cognitive work that leads to radical discoveries. And we are already seeing the early signs of this saturation even before we hit that 50-year theoretical boundary.
And Lem offers this really powerful historical comparison to illustrate this early saturation.
He does. He says, decades ago, a truly major, unexpected discovery, like, say, the isolation of X-rays by Röntgen, it had a unifying effect on the community.
Everybody jumped on it.
Everybody. It was so foundational and so paradigm shifting that it mobilized a significant portion of the entire world's physics community. People literally dropped what they were doing and rushed to this new frontier. It was a massive unified field response.
Okay, but if a comparable fundamental discovery were made today, let's say room temperature superconductivity was unlocked tomorrow, what would happen?
The response would be completely fragmented. A discovery of comparable magnitude today would attract only a tiny fraction of a percent of all physicists or chemists or biologists.
And the reason for that diminished attention span isn't that scientists are less curious, right?
No, not at all. It's that the scientific research front has expanded so enormously. They literally cannot afford to stop specializing.
Right.
We have multiplied the knowledge base by 10,000, and in doing so, we have expanded the research front into countless tiny, hyper-specialized sectors. The number of people available for any single sector is diminishing proportionally because everyone is already specialized and busy exploring their own tiny, rapidly expanding sliver of the frontier.
And to jump fields now requires years of catching up, which is basically career suicide for a lot of people.
You can't do it. The consequence of this diminishing attention is twofold. First, a major discovery might lie dormant for years, just waiting for someone with the right narrow expertise to fully appreciate it.
And
Second, the lack of available people will lead to an increase in phenomena that require study but are currently being abandoned by researchers simply because no one has the bandwidth or the institutional support to chase them.
so theoretical development won't just stop cold.
No, it won't stop, but its pace will inevitably drastically slow down. The theoretical faucet won't turn off, but the pressure will drop dramatically. And that will lead to decades where the great unifying theories become increasingly rare.
And this change in pressure, this deceleration, this is where the most severe long-term societal problems really begin to emerge.
So if the tap of new theoretical discoveries starts to slow down because of this fundamental human bottleneck, what keeps civilization going?
Right, what happens next?
This brings us to the analysis of the crucial buffer zone and the grave choices that lie ahead when the momentum starts to fade.
The good news, at least initially, is that we have a temporary cushion built into the system. Lem calls this technological inertia.
Yeah, and the fact is, throughout history, theory has constantly outpaced industrial realization. We know how to do vastly more things than we have actually implemented commercially or industrially.
The gap between theory and implementation is the buffer.
It is the buffer. Think of something like fusion energy or deep molecular engineering or advanced material science. We have the foundational blueprints, right? The theoretical reserves are there. But we lack the final breakthrough in scale or cost or engineering complexity to make them widely available.
So even if the growth of theory were to stop entirely tomorrow, like as every university shut down,
A complete halt.
the accumulated reserves of knowledge, all those unutilized blueprints sitting in academic journals and research databases, would be enough to fuel technological progress for another 100 years.
At least. This is technological progress proceeding purely by inertia. It's just feeding off of the gathered but as yet unutilized data.
And that 100-year buffer is a massive safety net.
It is. It means the immediate consequences of scientific saturation won't be felt instantly, which of course often leads politicians and society to underestimate the long-term danger.
Because the problem is always 100 years away.
It's always someone else's problem. However, the source immediately contrasts this buffer with the ongoing, non-stop pressure of global population growth.
And that contrast is critical because it highlights the moral and practical disaster that's waiting for us. I mean, currently, global technological progress is growing quickly, maybe 6% per year globally?
Something like that, yeah.
But despite this incredible growth, the needs of a massive portion of humanity are still critically unmet. We're talking access to clean water, basic medical care, reliable energy.
The basics of a modern life.
So, if technological growth slows dramatically due to scientific saturation, if it perhaps settles at a linear or even a sublinear rate while population growth continues,
The effect would be catastrophic.
Yeah.
Absolutely catastrophic for those people currently waiting for technological advancement to improve their lives. The inertia only helps the rich world catch up to its own theoretical potential.
So for much of the planet, it wouldn't just be stagnation, it would be the beginning of an accelerating regression.
Yes, because if the technology gap becomes fixed, it becomes permanent, and tragically, it keeps widening.
And this impending slowdown is precisely why the future situation causes such anxiety among the scientific planners that Lem references in the text.
They see it coming. They foresee a painful position where the scientific community, or let's be honest, more likely politicians and funding agencies, will be forced to make these agonizing decisions.
Which research must be continued and which must be stopped?
They have to choose where to allocate the single scarcest resource, the highly specialized human mind.
And this leads directly to the most crucial dilemma of this whole post-explosion phase, doesn't it? The Great Research Lottery.
The Great Research Lottery. The anxiety stems from a foundational observation of scientific history. The entire history of science shows that the great technological leaps, the kind that fundamentally restructure civilization, like electricity or computing,
The big ones.
the big ones, they originate almost exclusively from pure research that had absolutely no practical objectives when it began. The work was done out of intellectual curiosity. It was often dismissed as esoteric or completely irrelevant.
We're talking about mathematicians working on abstract equations that suddenly turn out to describe reality perfectly 50 years later.
Right. Or physicists chasing non-commercial questions about atomic structure that lead to everything from medical imaging to power generation.
Yeah, a perfect example is James Clerk Maxwell, right?
Perfect example. He was working on purely theoretical equations to define electricity and magnetism. He wasn't trying to build a better telegraph. He was trying to unify two fundamental forces of nature. His theoretical work, pure math, predicted the existence of electromagnetic waves that travel at the speed of light.
Decades before anyone could prove it.
Decades. It was only later that Hertz proved they existed, and even later that Marconi industrialized them into radio. Pure research delivered the prize.
And the reverse process, where a practical, immediate need drives a great fundamental theoretical discovery, the source notes that's an exception.
It happens, but it is so rare to the point of being unreliable. If you need a breakthrough, you cannot rely on practicality to deliver the theoretical foundation.
And this historical pattern, this is what creates the impossibility of rational planning.
Exactly. It has historically been impossible to predict which theoretical pursuits will yield valuable technological results 10, 20, or 50 years down the line. We can't predict the breakthrough because, well, if we could, we would have already made it.
And this is where the lottery analogy becomes such a powerful visualization of the risk society faces when it's under this kind of resource constraint.
Imagine a lottery with 1 million tickets available for purchase.
Okay.
And hidden among those 1 million tickets, there are 1,000 winning ones. 1,000 fundamental discoveries.
Right. So if society, metaphorically, buys all the tickets, meaning we fund all available theoretical research, no matter how niche or esoteric it seems.
We guarantee winning all the prizes. We get those 1,000 fundamental discoveries that will fuel the next 100 years of technological inertia. We're safe.
But if in the future, due to this human resource ceiling, society can only afford to buy half of those tickets, or it only has enough specialized labor to staff half of those theoretical pursuits,
Then there is absolutely no guarantee that the half we picked includes any of the 1,000 winning discoveries.
we might end up winning nothing. You risk abandoning the very sectors where the biggest, most unforeseen breakthroughs were lying in wait.
The entire history of our progress suggests that the theoretical line of inquiry that looks the most useless today might be the source of tomorrow's ubiquitous technology.
And when the future requires choosing which research sectors to bet on based on perceived immediate utility, focusing all our resources on immediate climate solutions or medical breakthroughs,
Which seems so rational.
so rational.
Yeah.
But society risks abandoning the very fields that would prove to be the most fruitful. By definition, those future breakthroughs could not have been foreseen by the planners who are making the cuts. It's a fundamental, unsolvable problem of allocation under scarcity.
And what's really chilling is Lem's observation that the world was already experiencing the start of this gambling decades ago, even when the human resource limit was still theoretically far off.
How so?
The observation was that the heavy concentration of specialists and funding in fields that were deemed strategically critical, things like rocketry and atomic research during the Cold War,
Right.
was causing other vital scientific branches to suffer. Money and people flowed to areas with guaranteed immediate military or political utility.
So the lottery has already begun. We are already choosing to buy only certain tickets.
We've been doing it for a long time, so if we were already cutting pure research based on perceived utility decades ago, just imagine the existential pressure when the human labor resource hits that absolute ceiling and the technological inertia starts to wane.
The choices become not just economic, but existential for global civilization.
It forces a confrontation with the true cost of progress. Unlimited curiosity, which drove the explosive phase, is a luxury that a saturated, constrained civilization may no longer be able to afford.
So what does this all mean for the human endeavor? This isn't a prediction of some Hollywood civilizational collapse, right?
Yeah.
There are no meteors, no pandemics in this model.
No, it's quieter than that.
It's a prediction of a fundamental systemic change in the very character of civilization itself.
It is the transformation of the system's dynamic characteristics that matters most. The point where that growth curve bends from an explosive skyward ascent to a curve of saturation that signals a profound, inescapable change in the nature of science and society.
Science won't just vanish entirely,
Yeah.
but its current form, the look of unrestricted, self-accelerating growth, that will disappear.
Yes. Lem suggests that this 300-year explosive phase, which we've celebrated as this constant, boundless progress, is simply a transitional, momentary stage in the long history of civilization.
Just a flash in the pan.
A very bright flash, but a flash nonetheless. And this transition, it forces a painful confrontation with our own intellect. Must the versatility of reason's aspirations, the ability to study anything and everything regardless of utility simply because it exists,
The thing we value most about science.
the thing we think is its defining feature, must that give way to a bundle of directed, targeted, pragmatic actions?
The implication is profound. A civilization saturated with knowledge but strictly limited by personnel is forced to become entirely utilitarian.
It has to.
It must only pursue lines of inquiry that serve an immediate, known, justifiable purpose. It loses the ability to afford serendipity. It forfeits the unpredictable, accidental discoveries that drove its initial explosion in the first place.
That's the real tragedy of saturation. The civilization becomes trapped by the sheer weight and complexity of what it already knows. Every specialist is required just for maintenance and known research. There is no capacity left to chase the wildly impractical, theoretical long shots that provide the eventual breakthroughs.
They become victims of their own success.
Perfectly put.
And this shift in dynamic characteristics is perhaps the most significant transformation since the Industrial Revolution began. The very purpose of science changes from open-ended exploration to managed maintenance and strategic application.
And this final insight brings us back, full circle, to the cosmic questions we touched on at the start. The concept of this rapid exponential growth sheds a special and, frankly, a terrifying light on the problem of stellar Sekazoa
Intelligent life across the stars.
and the great silence we observe.
Right. If we assume our civilization's trajectory is typical, that this hyper-accelerated phase of knowledge accumulation happens elsewhere, then the silence of the cosmos takes on a new, really chilling meaning.
This rapid explosive growth, the kind that constantly doubles its output, it can last for millennia, sure, but it absolutely cannot last for millions of years. It's mathematically impossible.
So on an astronomical scale, this entire growth phase lasts an instant.
An instant. It leads to an incredibly rapid cumulative chain reaction of knowledge creation.
Which makes the 300 years of the Industrial Revolution and its scientific feedback loop just a momentary flash, a cosmic firework.
Exactly. And a civilization that exhausts its human resources in this scientific explosion is comparable to a star that burns its substance in one flash.
Wow.
It consumes itself violently to produce an immense but very short-lived light. It has traded longevity for maximum intensity.
And after that, flash fades. After the fuel, the raw, available human mind is exhausted. What is left?
After the flash, the star either settles into a state of changed equilibrium, a quieter, cooler, more stable, but profoundly non-expansive phase, or, and this is Lem's warning, it becomes the arena of degenerative processes that may have silently extinguished more than one cosmic civilization entirely.
So the very dynamic process that we assumed was a sign of eternal vitality might, in cosmic terms, be the sign of a system reaching its peak burnout.
And entering a state of necessary but profoundly altered stasis.
Where creativity gives way to management.
The irony is that the speed and the volume of our success today is the very engine dictating the future limitations we will face tomorrow. We created a system that demands more human input than the planet can eventually provide.
So this discussion ends not with some technological solution, but with a necessary reevaluation of what progress even is. We've shown that the physical universe may be vast and full of resources, but the human mind, the central actor in this whole scientific enterprise, is not.
It is finite.
If our civilization's dynamics, its 300 years of exponential explosive growth, are just an instantaneous flash relative to the universe's timeline, the profound question remains: what state of changed equilibrium awaits us when the light of that explosion fades and the human limit is finally met? What does a high-technology civilization look like when its purpose is no longer defined by limitless expansion and unpredictable accidental discovery, but by the necessity of managing, maintaining, and pragmatically applying the vast, unmanageable wealth of knowledge it already accumulated?
A profound question.
When the ultimate goal is not to find something new, but simply to keep the existing lights on. That is the question of the saturated civilization, and something for you to mull over as you look toward the next 50 years.